Okay, welcome to differential equations here. So this is our first lecture. This is going to be for section 1, maybe section 1.2, but we'll see how long it takes here. Okay, so just basic stuff here. We have a differential equation. By the way, I've been using this for about a year, and this is about the best my handwriting gets. So I apologize for that in advance. But a differential equation is simply an equation, okay, that contains a derivative. Okay, that would be something like, say, y prime plus y is equal to x, right? It's an equation. There's an equal sign. We have x's and y's. We have a derivative. It's a differential equation. Okay, so we break this down, okay, in a couple of different ways. So this first part is just going to be like what to call them, what are their names, and how do we distinguish between the two of them, because different types of equations are going to have different types of solutions, different techniques associated with them. Okay, so the first thing we're going to talk about is what this class is about, and if I could spell ordinary, that would be helpful. So we have ordinary differential equations. And these are differential equations that pretty much have one independent variable. Okay, so there's only one independent variable. Usually it'll be x or t, okay, because there's a lot of physics that goes on with this, so we take a lot of time derivatives, so that's what we're talking about. This right here, this is an example of an ordinary differential equation. Okay. In contrast with partial differential equations. We will barely scratch anything that even resembles a partial differential equation. These have a partial derivative in them. Okay, these are much harder. So if you've taken Calc 3 and you've dealt with partial derivatives, there's one section where we deal with partial derivatives, but we kind of turn it into like a partial derivative of x and y and then just go with that. But we really don't deal with PDEs in this class. We just deal with ODEs. Okay, that's pretty much our differentiation here. Examples, right? We have one. If we have something like y double prime, right, plus say 10y prime. Let's see, how about minus, we'll do a plus 9y is equal to 0. This would be an ordinary differential equation. This would be an ODE. Okay. X, y double prime plus 1 minus x, y prime plus 3y is equal to 0. Again, ODE. Okay, they don't have to be 0, right? I could have also said something like, we could have an e to the x over here. Okay, still an ODE. Okay, still ordinary. If you contrast this with what one more thing, just to make sure that we're doing this right, dx by dt plus say dy by dt is equal to say like x minus 5y, still an ODE, because even though we have two dependent variables, right, we're going to have a function of x and a function of y, we're only taking derivatives with respect to t, so since we only have one independent variable, this is still an ordinary differential equation. Okay. If you were engineering, physics, right, a lot of times they'll write this way instead. Right, this is the Newton notation where they use a dot. I tend not to like that. I like this one because I was a math major, but I know a lot of engineering classes use the dot notation because, again, it's all derivatives with respect to time, and it's just easier for them to do it that way. Like, okay, that's cool. but I typically, like this one or this one instead. If we have, right, partial differentials, notice the partial derivative, okay, x squared y, and then plus d squared u, and then partial with respect to y, and say equals 0, okay. This would be a PDE, even though, again, we only have one dependent variable, one dependent function. We have two independent ones, right? We have a partial of x and a partial of y, all right? Let's see if we did just go off the rails here. Something like that. This is, again, a PDE. We have partial of u with respect to partial of x, partial of v with respect to partial of y equals xy, and then that would be how that goes. Excuse me. Okay, so those are the nomenclatures. Mostly we're going to be in this realm. Okay, PDE is its own class and has its own techniques. And like I said, with a very small dip into this, we're not really going to touch this too much. Okay, the next thing we'll talk about is order. Okay, and this is pretty much this. How many derivatives did you take? Okay. If we have like a y prime is equal, or how about plus xy is equal to e to the x, this would be a first order. We took one derivative. Okay, y double prime plus say 5y prime plus 6y is equal to how about x squared. Well, let's not do a squared. I don't want you to get, I want to confuse it like that. How about a cosine? This would be a second order. We took two derivatives. Okay, that's all there is to that, so that's not so bad. Let's see here. Okay. Let's see. We could talk about. They'll talk about normal notation. Okay, putting it in normal form. You have a y double prime, say, equals an f of y prime, y, and x. This would be normal form. This is mostly used when we talk about how to make a computer do something. So in this case, right, we'd have y double prime is equal to negative 5y prime minus 6y plus cosine x. This would be the normal form. Okay, there's several forms that we're going to have to deal with, mostly dealing with the coefficients. Okay, but this is a common thing for, especially for setting up a computer program to run your solution. It's going to want it like this. Okay, most of the differential equation solvers that we have. Okay, let's see here. We could look at linear. We'll deal with some nonlinear stuff. A lot of the class has to deal with linear equations, but there are nonlinear ones. Again, there's different techniques to solve both of these, and that's pretty much what we're dealing with. This only applies to the y variable. Okay, so if you remember back from algebra, if I gave you, like, say, y was equal to the square root of, or not the square root of x, I don't want to do that. If I want to say y is equal, say, to the square root of 3 times x plus pi, and I said go ahead and graph that, or what kind of an equation is this, right? To somebody who's in algebra 1, this makes it terrifying, but it's still, right, it's still y equals mx plus b. I'm not going to fool you. You're going to say, well, that's a line, it's linear. Even though this coefficient isn't really a linear, it isn't a nice number, and this is a square root, so this is not a linear, like, number, like it's not an integer. But we don't care. Okay, we don't care what those coefficients are. Same thing applies, except now you have to, like, boost it up by one level. Okay, so if we do like a square root of x, y double prime, plus sine x, y prime, plus say, well, I would not want to solve this, okay, is equal to e to the x. This would be linear because, right, all the stuff with y's in it only has one power, okay, and there's no interaction between the y's or its derivatives, okay. So this would be linear, like, well, but the x's, like, we don't care about the x's, okay? The x's do not have any bearing on whether or not this is linear, okay? This would still be a pain to solve. But if we did something like, say, y times y double prime is equal to e to the x, well, even though that's not really a terrible equation to solve, this would still be nonlinear, right? This is just, you know, y times d squared y is equal to e to the x dx squared, right? Yeah, it's like a calc 1 kind of a thing, where you just integrate both sides twice, or calc 2 rather. You integrate both sides twice, and you'll be able to get an answer here. But it's not linear because there's a y times a y double prime. Okay. Similarly, if I did this like y prime plus sine y was equal to say 6, not linear, mostly because the y is inside of a sine function, and that's not a linear function. Okay, so you could have a coefficient, that's fine, right? If I said y prime plus say 6y was equal to, you know, x, that's fine as a linear because the 6 is linear, right? I mean, the coefficients don't matter, right? Even if it was a crazy, you know, e to the x square root of x, y, and then pick something terribly nonlinear, right? Again, I wouldn't want to solve this. This is going to be hard, but it's still a linear equation because the y and the y primes are both linear. Okay, so y plus, like, say, y squared is equal to x. Now it's nonlinear again. Okay, so that's between linear and nonlinear. Okay, so I'm going to do this. Okay, so that's pretty much what we're talking about with all the classifications. So we have you know, ordinary differential equations, partial differential equations. We have linear versus nonlinear, and then we have the order, which is how many derivatives have been taken. So that just pretty much I think the first part of the homework is pretty much going to ask you classify this as, you know, what is this, right? So they'll probably give you something like y double prime squared plus y is equal to e to the x, and they'll say, what is this? And they'll say, well, this is a second order nonlinear ODE. Okay, so this is a second order because we took two derivatives, nonlinear because one of the y terms is squared, and then we don't have any partial derivatives here, so this is an ODE. Okay, and that's just what they're going to ask you for the first little part of that. Okay, I think what I'm going to do is I'm going to stop here to keep the lessons a little bit short, and then we'll do 1.2 in a minute. Okay, so let's go with that.